In this video, we're starting a new topic in the class, and that topic is torque. So to introduce torque, I wanted to first think about forces for a moment. So we learned back in chapter 3 and 4 that forces on an object change the velocity of that object or cause an acceleration. So this is kind of an analogy I'm going to write. Forces on an object change that object's velocity v. Torques on an object, one or more torques, change that object's rotation. So there are equations for rotational kinematics, so to describe the rotational velocity and angular position of objects as they rotate. We're not going to worry about that in Physics 106, but we still do want to understand how these torques work, and eventually what we're going to learn is how to deal with how these torques behave at equilibrium, which lets us solve a whole new class of problems. So torques are the things that can change the rotation of an object, but torques don't exist by themselves, isolated from other things. In Physics 106, torques are created because of a force. So forces change velocity, torques change rotation, but torques come from forces. I guess I should write that down. So they're caused by forces, and where that force acts on an object is important. So contrast this with when we're doing free body diagrams. When we're doing free body diagrams, no matter if the rope is tied to the bottom of the block or the top of the block or whatever, when we draw a free body diagram, we draw all of our forces as coming from a single point, right? We don't care about the size or shape of the object. We just draw the object as a point and the forces as vectors coming from that point. When we're dealing with torques, now the location of that force matters. So that is something that we're going to have to keep track of. So in other words, to sum up, for forces, we can treat our object as a single point and treat all of our forces as coming from that point. For torques, we now have to pay attention to where those forces are. Okay, let's do a little demo of a torque just as an introduction. So here I have a plastic meter stick. It is pretty stout. I'm not going to really be able to get the whole thing in the picture very easily, but I want to show you one thing. So here, I'm going to hold this end up with one hand, and if you hold it at the very end, it's actually pretty hard to support all of the weight of the meter stick. It's a lot easier if you push it up from the bottom as well. I'll do it like this so you can see it better. So I can push my finger up on this at different points, and all of these points allow me to hold up the meter stick. But you'll note, if you try this on your own, the closer you move your hands together, the harder and harder it gets to hold the meter stick up, or more specifically, the bigger and bigger a force I have to push up with this finger in order to keep the meter stick from falling down, until at some point here, if I get them close enough together, this is actually like painful to my index finger. This is painful to keep this meter stick supported. So in other words, this is a clue that the amount of force it is taking me to hold this meter stick up is changing. And that's something that we're going to be able to explore with torque, why the location of this force is something that matters so much. All right, great. So before we get to how those more sort of some complicated things work, let's get to some very simple definition sorts of things. All right. So for a particular force, the torque from that force is given by the following equation. So so our torque is a Greek letter tau, lowercase tau. So I draw that like a lowercase t, but instead of crossing it in the middle, I cross it at the top. That is something like how it's drawn in most textbooks. So our equation for the torque is R times F perpendicular. And now before we go further, we kind of have to define what's going on with these. So our variable R here is the distance from a designated point called the center of rotation. Or we can also call that the rotation point, to where the force is acting. And this rotation point is important. We'll go over this again in a moment, but torques have to be defined with respect to this rotation point. Kind of just like how our x and y coordinates need an origin, our torque calculations all need a point that they are being calculated from. The torques around this point, or the torques relative to this point. So R is that distance from that point to where the force is acting on our object. F perpendicular is the component of that force that is perpendicular to this distance R. And we'll draw a picture here to illustrate this. I'll erase everything except for the equation, I guess. That works. So the classic example to use for a torque problem is like a wrench turning a bolt. This is also a place where you encounter torque numbers if you're working on cars or machinery. How tight to tighten things is often specified as a amount of torque. So let's say we have a square-headed bolt. So this is like going into the board here. You know, we've screwed it into the board or something, and we have a wrench around this that we are using to turn. So let's say we are exerting a force on this wrench downward here that is equal to 11 newtons. And let's say this is the center of our bolt right there. And let's say this distance is 0.4 meters, and the length of the whole wrench is 0.6 meters. So this is a pretty big wrench. Much, this is a 1.5 foot plus long wrench. Okay, so what is our torque in this situation? Okay, so here, our center of rotation is at the center of this bolt, the point that we would rotate around if we turned this wrench. Our force is 11 newtons, and now remember, this R is not the size of our object. This is just how far away our force is from the rotation point. So this 0.6 meters was, to distract you or something. This 0.4 meters is the only thing that matters. It doesn't matter how long this wrench is, how much further it keeps going for. The only distance that matters is the distance from here to here, which is our 0.4 meters. So R is equal to 0.4. F perpendicular is the component of F that is perpendicular to R. So the way that I've drawn this, if this distance is R, our force F is perpendicular to that. So F perpendicular here is all 11 newtons. That doesn't necessarily have to be the case, but in this case it is. All right, so to calculate our torque then, we multiply our 0.4 meters by our 11 newtons, and we get 11 times 0.4 is 4.4. And our units are newtons times meters, which we are now going to keep as Newton meters. So remember, 1 Newton times 1 meter was also what we used for 1 joule of energy when we learned about work. However, torque is not energy, and Newton meters for the purposes of torque, are kept as their own thing. So 1 Newton meter of torque is the amount of torque, this rotational kind of force-like thing. 1 Newton meter of torque is how much torque you get from a force of 1 Newton at a distance of 1 meter away from this rotation point. All right, great. So this is a simple enough example. Let's make it slightly more complicated. For this same wrench, this is a different wrench actually. For a different wrench, but almost identical, if this wrench is, let's say our force is acting 0.5 meters away. Sorry, this is getting kind of illegible. 0.5 meters away from this rotation point, we have a force on the wrench that is acting at some angle. So our force now is not perpendicular, it is at an angle of 20 degrees, and our force is 20 newtons. So now, what is our torque? Well, our torque is still R F perpendicular. F perpendicular now, if our force is like this, the perpendicular component is this vertical one. So this component is what we want. That's like Fy. We can also call it F perpendicular, either way. So that is going to be, if this is our 20 degree angle and this is our 20 newtons, this is going to be, this adjacent side is 20 times the cosine of 20. Which is equal to 18.8 newtons. So of that 20 newtons, 18.8 of it is in this perpendicular direction. Multiplying it by our distance r, that is 0.5, we get a torque of 0.5 times 18.8, which is 9.4 newtons. I wrote 9.4 newtons, but clearly the answer should be 9.4 Newton meters. All right, great. One last equation I want to give you. So this equation works for all the torques we need to calculate in this class, but sometimes it might be more convenient to use it in a slightly different form, and that is the following. Our torque is also equal to R F sine theta, where, and this is very important, just like how in our work equation theta meant something, FD cosine theta meant something very specific. In this torque equation, theta also means something very specific here. So here, theta has to be the angle between R and F. So in other words, for this example, like we just did here, our R looked like this, our force looked like this. This angle was 20 degrees, but the 20 degrees would not be what we plug into this equation because the angle between R and F is not 20 degrees. It is 20 plus 90, it's 110 degrees. Or you could also say the angle between it is over here and is 70 degrees. Either 70 or 110, actually, it turns out, gives you exactly the same answer, so it doesn't matter. It doesn't matter, but we'll stick with this picture because it's simpler. So the angle between the force and this distance R is 110 degrees. And so 0.5 times 20 newtons times the sine of 110 degrees also gives us the same 9.4 Newton meters of torque.